So hi everybody. I guess all of you are the survivors that have made it this far in the class, so good for you. Made the cut. My name is Andrew Henderson, and I'm one of Dr. Ian's students. I've been in his lab for about 2 years now, in my third year. And he asked me to come in and speak with you a little bit about some of the work that I have done with Android and the internals of Android and Android on embedded systems. It's the mobile OS class. Most of what you've covered so far has been Android specific, but I think that you're going to find that a lot of the fundamentals are pretty much the same across all the various platforms. In particular, anything tied to the ARM architecture, because that's kind of taking over the embedded space as far as embedded devices, not just mobile phones, but tablets and all sorts of various odds and ends, especially with the rise of the single board computer and the system on chip that all use the ARM core and ARM instruction set in it. You're going to find that it's being used a lot more in the mobile space. So anyway, what I'm going to talk about today is we're going to run through a few bits and pieces about the kernel that's used in Android and actually how it's tied to Linux. A lot of people don't quite understand how closely coupled Android is with Linux in many respects. We're going to talk about that a little bit. And also how Android gets up and running, because until we actually get to the init process of the Android startup, I mean, essentially you're running Linux at that point until you get up to that point. So we're going to run through that and kind of give you a high-level lay of the land, because I'm pretty sure in every class that you ever take here that mentions Android, you're going to see that same layered diagram on the blue background that you get from android.org or whatever. You've seen it in every single class. That's like a static snapshot of this is the whole system. But I'm going to present it more in a chronological order. This happens, then this happens, then this happens during setup. So you can kind of see what the flow is in that regard, rather than just a high-level view of the whole system architecture. And this past summer, I got a little bit famous on the internet because I ported Android to this BeagleBone Black platform in a class for Dr. Do, which he was ecstatic over. And everybody used it for their products and everything. It was great. But it ended up with me getting like thousands of emails from people all over the world asking me, how do I do this, how do I do that, and everything. So I'm going to give you a real quick rundown on that. And I actually have some YouTube videos that I've put up of the system running with different hardware and things, so people can kind of get an idea of what works and what doesn't. And then I'm going to talk a little bit about my favorite subsystem of the Android kernel edition, which is the Binder IPC. It's the IPC mechanism that Android uses for things like intents. So it's very important from a security standpoint because it's really where all the various pieces talk to each other. So it is a subsystem that is really worth looking into if you're interested in security, just because if you're trying to investigate mail fraud, knowing how the U.S. postal system works is probably a good place to start. So it's kind of the central switchboard and message passing mechanism. So we're going to look at that a little bit. And then we'll give you a couple resources if you're interested in looking a little bit further, and learning a little bit more. And of course, you also have the people that are here in the lab. You're always welcome to track me down if you can find me. I'm pretty elusive to ask your questions. I know there's plenty of you that already do, that know me, and that's fine. But most of the students in Dr. Ian's lab are very knowledgeable about this sort of thing, so they'll be able to help you out if you need more information. Okay, so real quick, the Android kernel is actually a Linux kernel with just a few extra subsystems added into it. If you take a look at a Linux kernel that has the additional Android drivers in it, it's really only about an extra 25K in the compressed Z image binary that's created. And you can actually run an Android kernel on your desktop, on your Linux. You'll have a couple extra entries into /dev in the file system. And you'll see a few other things in your D message and your system log when you run it, where you can see the Android subsystems running. But if you want to be an OS hipster and say, well, I run Android on the desktop, you can. You can run an Android kernel. Just enable those few extra features. It won't hurt anything from the Linux side of things. Okay, so it used to be that the Android was a series of patches to the Linux kernel. So it was kind of maintained separately, and then if you wanted to build Android, you took whatever the current Linux was, whatever the main line was, and then you patched it with the additional Android features that you wanted or needed in order to get the system up and running. As of Linux 3.3, that was all merged into the main line. So now you don't have to go hunting for Android. It's included in the Linux kernel source base itself, which makes it a lot easier if you want to experiment with it, and you don't have to try to patch it into a kernel that you're interested in. Okay, so the important thing to take away from all this, if you are developing an Android system and you have the appropriate Linux drivers for whatever hardware you want to port this system to, you've done it. You're there. If you have a driver that runs under Linux, it will run under Android. If you have firmware for things like, and on Capeboards, the device tree that's in newer versions of the Linux kernel, anything like that, it will work. It will work under Androids, assuming that you have the user space components that take advantage of it. From the kernel's point of view, all of these are exposed and available. So device drivers, because device drivers are so well supported under Linux as a whole, for some things, common hardware, that if you're porting Android to one of these platforms, all the pieces are already there. You just have to kind of hook them up and get them talking to each other. Okay. Does anybody recognize that application? You should. You should if you're graduate students. This is the utility, the Kconfig utility that's used to configure and build the Linux kernel. If you haven't ever built a Linux kernel, shame on you. You should at some point. Everybody gets everything these days, but you should try to build a kernel from scratch sometime, because it's kind of an important part of, your growth as a computer scientist. I know in the OS class you work with FreeBSD, and this is really a bit crazy compared to FreeBSD when you build it for yourself, just because there are so many options. If you turn off the wrong thing, and all of a sudden all these things don't work and everything. It's not the easiest thing to use, but you should get exposed to it at some point. But anyway, it's structured in a hierarchy. You start at the top level, you go into device drivers, and then step down and step down and step down, and enable or disable as needed for the features that you need. Then you build your kernel, and then everything that has an asterisk is statically linked into the kernel. For some of these, you can set them up as a module as well, and then dynamically load them. And it's a similar mechanism under Android as it is under the Linux kernel. You can actually dynamically load modules out of the file system, though generally you're not going to see that. If you get a commercial Android device, module loading is actually configured off, because it's one more thing that the manufacturer knows exactly what hardware is on that Android phone and what they're tailoring the kernel to, and the hardware abstraction layer and everything else involved with it. So they're not going to have dynamic module loading turned on. But if you're building your own Android system, you certainly can. There's nothing stopping you from doing that. So if we step down through the various levels of the architecture here of Kconfig, you'll see that under staging drivers there's a section called Android, and then various Android features. That is Android as far as the kernel is concerned. If you turn on all these features, you have everything that an Android kernel is going to need. And there you have the shared memory manager, Binder, of course. You've got the low memory killer, everything that you need. And then this is also for an ARM setup. So there's the Android Time GPIO driver, where it can set up a timer on one of the pins coming out of the main processor chip as well. That's kind of ARM specific. So you'll see lots of reference to this if you're looking through like any embedded Android type stuff, and the first thing they'll say is just turn all this stuff on, because it just turns on all the Android features in the kernel. Okay, if we take a look at the Android boot sequence, your processor is hard-coded to start executing code at some point when it starts off, all right? And that's really the point where your bootloader, if you are an old school Linux person, then you're probably used to Lilo. These days, most systems use Grub for your desktop Linux PC. U-boot is what is typically used on ARM platforms. U-boot's kind of a generic bootloader that has support for a lot of different embedded platforms. And it's the one that I'm most familiar with on these platforms, just because it's so common and so well supported and has a ton of features. But once the CPU begins executing, it's immediately going to go to a specific memory location, in order to grab the bootloader and start executing. So this bootloader up top is U-boot, and its purpose is to get the hardware in a stable state and then load the kernel into memory and start it executing. At that point, its job is done. So as long as it can find the kernel, you're off to the races. From the bootloader, we move into the kernel itself, which is standard kernel initialization. All the subsystems are initialized, all the device drivers are loaded. Bootstrapping of the kernel, once you get past this point, you're pretty much clear as far as kernel and bootloader are concerned. Everything else will occur in user space or pieces of software in user space that are interacting with the kernel to initialize. Now, if you've taken the OS class, you know that a Unix kernel will start executing. The very last thing it does as part of the bootstrapping process is it will execute an init process. This is kind of, you could think of it as the program for the kernel. When init exits, the kernel exits. So once you get into the init process, it will never exit. It will run forever. If you actually exit the init process, your kernel will panic and your system will freeze. So the last thing that the kernel will do during the bootstrap process is it will execute an init process. And then the init process is responsible for executing a series of startup scripts that start all of your system daemons, that start everything running in the system in the background. Things like mounting file systems and starting daemons to monitor the network, get the network interface up and running, all the things that make an actual running system. So if you're thinking of like really locking down a system, the daemons and the system services that init starts up are where you start. That's where you start shutting things off. If you are familiar with init.d, run levels, things like that under Linux and Unix, that's what the init process is sweeping through. It's looking at all those starting scripts and telling what services to start and what not to start. In this case, under Android, this is where we really start to part ways with Linux. Everything in the user space is quite different under Android than it is under Linux. Because Linux has a very standard hierarchy for starting things, daemons it starts. Android has this complete other set of daemon services that run in the background. Now some things like the file system itself are implemented using drivers in the kernel. So they're still going to be the same. You're still going to have the same permission mechanism for user group world, same type of directory structure. If there's a problem and there has to be a file system check, those sorts of utilities are still the same because the way that those file systems are implemented in the kernel are still the same. So once we get past init and we start getting down into these native daemons, these are the various things that are going to be running in the background that make Android Android. And the one that you are probably most interested in is this app process, this Zygote. Zygote sets up the Dalvik virtual machine that's running. And every time that you start a new process, rather than creating a whole new Dalvik virtual machine, loading in all the class files and everything, a call is made to the kernel, a syscall, to just fork the process. So it just makes a copy of the memory, and then it's just copy on write. Anytime that there's a modification to memory, new memory pages are allocated at that point. So it allows new processes to start up quickly without having to start up the Dalvik virtual machine and load all these things off of the file system and all that. It just makes a snapshot of it and clones it and then goes from there. So if you are studying a running Android system, you are most interested in all of this on the right here. From this box that will then fork for the new app and all of the communication inside the system. But from my point of view, the sort of things that I work on, I'm interested in this piece up here in the corner, on the upper left corner, where the system just gets started and running. If you are interested in securing Android or studying Android from the user space, your work will most likely start here in the lower left corner with these native daemons. And then this is the Dalvik virtual machine that's running inside of the Zygote. So if you're interested in making a more secure framework, if you want to make it so when you are calling functions inside your Java program that's running in this Dalvik virtual machine, and it calls more secure versions of the framework, this is where you're going to be looking, and this is where you're going to be looking in the Zygote and the native daemons. Okay. Now my claim to fame. Okay, as I mentioned, over the summer, I was working with this BeagleBone Black platform. It's a great little platform. It's only about the size of a credit card, much larger than it is in real size or in real life. This board's only about $45, so it's a great way to get started with the ARM platform. And very powerful, 1 gigahertz processor on it, and it's a system on chip. So on this large chip that's here in the center, you have got all sorts of components beyond just the CPU itself. So it's really just a whole platform in one convenient small package. It uses HDMI out for video and audio. So just plug one cable in for that. It's got a USB port, so you can plug a hub into that, and then keyboards, mice, whatever you want, so you can make a full desktop out of it. So I took a look at this, and Texas Instruments makes the core chipset on this. This is kind of a joint work of Texas Instruments and the hobbyist community, the BeagleBoard.org community. And they had a old version of Android running on this. It's actually based off of the 3.2 Linux kernel. I mentioned earlier that as of Linux 3.3, Android is merged into the mainline trunk. So they are actually taking old work that they have done of 3.2 Linux kernel and backported a bunch of Android features into it to get it up and running. And this board, its base kernel is a 3.8 Linux kernel, because there are a lot of embedded system on chip, ARM platform fixes that are in the 3.8 kernel that aren't in the 3.2 kernel. So a lot of people were clamoring for TI to do a port of Android to this board, like a proper port to 3.8. And TI said, no, we're not going to do it. We're going to stick with 3.2. So I thought it would be a good exercise to port it to 3.8. Little did I know what I was getting myself in for. But anyway, this port really consists of 3 pieces, if you look at it. And 2 of them are much smaller than the third, but it turns out the 2 small ones are the difficult ones. And those 3 parts are the bootloader, the U-boot, the Linux kernel itself, and the Android system. Now remember, the Android system is everything running in user space. It's all the system daemons that are running, it's the Dalvik virtual machine, all that stuff. But it turns out, if that is designed properly, all that user space stuff is completely decoupled from the kernel itself, or the kernel's implementation. As long as the kernel is still exposing the same interfaces and /dev, and it responds to the same system calls in the same way, the kernel is completely decoupled from the implementation of what's done in user space. Okay, so the theory was I could pull out the 3.2 kernel, I could pop in a 3.8 kernel with all the Android goodies turned on, and it would just work. Well, it wasn't quite that simple. It did take a lot of doing, but conceptually that's what happened, and it does work, and it works quite well. There are some device drivers that are whirling the 3.2 kernel that weren't ported to the 3.8 kernel. So I couldn't turn those on. So I can't give you like hardware accelerated graphics and things like that. OpenGLES and things like that, just because TI has not provided the drivers for that. But overall, it was a good exercise and a good example of how decoupled the kernel actually is from the system itself. I took their complete build system from the Linux 3.2 kernel configuration that they had for Android, like all their user space stuff, and I just pulled all their make files and then just modified it to use a different kernel. And I had to tune a couple things in the file system to have it look in different places for things. But that was more board specific rather than implementation specific stuff. Okay, so what I'm going to do now is I'm going to move on to some internals inside the kernel. In particular, I'm going to talk about Binder IPC. Because like I said, this is kind of the control communication center for the entire Android system. It has components that exist in user space, it has components that exist in the kernel. So if you're looking for something that's Android specific, that's really holistic of the whole system, this is a good place to start looking, because conceptually it's pretty simple too. There's a lot of details, but understanding how it works is pretty straightforward. Okay. Now, Binder is actually based on OpenBinder, which has been around a while. I don't know if anybody ever ran BOS back in the day. It was awesome. It was like 15 years ago that B was going to take over the desktop, and it was like B, there was Linux, there was BSD, and they were all kind of fighting for kind of Unix systems on the desktop back around the .com era. But then everything just kind of died off. B is now lost to history. Anyway, the IP for OpenBinder was first developed at B and then later at Palm for Palm OS for embedded platforms, PDAs. But essentially, if you're looking at Binder, it is a file that's placed in the /dev file system, /dev/binder. You open this up, and then you read to it and you write to it, and it allows you to send messages to other parts of the system. Those messages are routed through the kernel, and then they can be explicitly addressed and then sent off. And you can pass objects, you can pass simple messages, all sorts of stuff. So it's really useful for what it does. And no software that is written on the system, like an app or something like that, is going to use DevBinder directly. Access to DevBinder really comes through the framework. So you are making calls, like you're sending an intent in Android. You're sending a message to some other process or to the kernel itself, sending some control message. And it will get eventually, once it goes through the framework, it will eventually get written to DevBinder. And then whatever responses come back will once again get read out of DevBinder and then percolate back up through, and then asynchronously provided to whatever activity needs it. Then you're running application. Okay? Like any device, you open it and then you use I/O controls to read and write from it. And the interface itself is really quite simple. There are only 5 I/O that control this thing. And when you open DevBinder, the kernel knows you're opening DevBinder. It looks at the thread ID, like process ID, for the particular thread that opens it. And it knows, okay, for this instance of DevBinder that's been opened, I'm going to map it to this thread ID. So I know anything that's coming in through this interface is coming from this particular thread. Now, I have not seen anything about multiple threads in the same application opening Binder. I don't think that happens. I think it's just one instance of opening Binder per Dalvik virtual machine, but I don't know that for certain. So this is the simplest picture, please excuse the one spelling error, that I could find that explains how Binder works, how this IPC works. And it's really pretty straightforward. You can think of it as the client as your application that's running on top. This is your Java app that's running. The proxy is going to be the framework that you're calling. So it's some sort of Java class file that's provided by the system that actually packages your intent, or takes your intent, pulls it apart, and then actually packages it as something to get sent. The Binder driver is /dev/binder, which sits in the file system, and also the component in the kernel that actually routes it to where it needs to go. And then you can think of server as kind of the opposite on the other side. We don't really care if it's going through a proxy or not. We just know that's the destination. That's where it's going. The destination may be in the kernel itself. It may be some specific activity in some other app that's running. It may be a service that's running. Like your app may request from the control manager to turn the volume down or turn the volume up. So it would send a service request out via an intent to say change the volume. And then the service would act as a deputy on its behalf in order to make that adjustment. Okay? But we can see that from your code, you're just calling a method. You're saying, I want to send an intent. And then the framework says, okay, I'm going to take all the data out of this function that you call that you've made, and I'm going to package it up properly in data structures for you. And then I'm going to pass it on to /dev/binder in the Binder driver, which will then do the unmarshalling. It'll unpackage it and figure out where it needs to go, and from there on, away it goes. And then if there's a response to come back, same thing, same process coming through. Now, during this whole time, from when you make the call to when you get this return, your application is blocking on this. Okay? When you do iocto calls, they aren't asynchronous. They are blocking calls because you are talking to the device driver. You don't want to just go away and tell the device driver, okay, well, when you've got something for me, let me know. You pass a data structure to it, and then you wait until it returns, and then whatever data you need is in that return data structure. Okay, and we'll look at that a little bit closer. So the iocto calls, there's really 5 that can be made. 4 of them are set up in configuration type things, like how long you're willing to wait, or if you're waiting for a response to come back from the other side, how long you're willing to wait. And the one that we're interested in is this binder write read, because that's where the actual communication takes place, back and forth. The other ones, yeah, you'll call them once when you set it up, or if you need to change the configuration for whatever reason. But binder write read is where the actual action occurs. So if you like thinking in C, this will probably help you picture this a little bit better. Though there's a struct binder write read, which is shown right here. You can think of it as, I'm going to have a buffer of data that I want to send via binder. It's going to be in that write buffer, and then write size says how big that buffer is, because you can't have the buffer null terminated or something like that, because you could be sending arbitrary binary data through this. So you have to have a way to tell exactly how long this buffer is. And then once we send it and we receive a response back, the response is going to be in this read buffer with, once again, the read size. So if you're sending a message that doesn't necessarily need a response, you'll get it'll come back immediately, and just this read size will be 0 because there won't be any return data. So if we create this data struct and we open up devbinder, read write, and then we populate this data with whatever we want to send, that's our message that we're sending out through binder. We call the ioctal with the file descriptor for the dev binder, the binder read write, and then the data that we're passing in. And then this ioctal call will block until it comes back. Now the data that is in this buffer, this write buffer that you send out as well as the read buffer that comes back, has a very definite pattern to it. Even though it's just a void pointer, it's just it could be any data that you want. The data is in the form of message identifier, an ID that says what type of message it is, and then a block of data. And then an ID, and then a block of data, and then an ID and a block of data. You can send multiple messages in the same buffer when you send it out. And in reality, this is what actually happens. There's a lot of additional maintenance stuff. There may be ref counting on objects that you're passing via this mechanism that you'll want to update that, and there are messages specific to that. So the identifier, data, identifier, data. Here's a partial list of some of the identifiers. So this kind of gives you an idea. It's just an enumerated int, so it's just a 32-bit int that gets dropped in there before each block of data. And you can see transaction and reply are the typical ones that you're going to see, that you're going to be interested in. That's where actual data is being sent. All of the rest of these, and this is only about half the list, by the way, all the rest of these have to do with just general maintenance of objects, ref counting, things like that, for if you're passing entire objects back and forth. When you have an intent that you're sending through this mechanism, you don't pick it apart and say, okay, well, this text represents this in the intent and everything. The entire object is marshaled and shipped off through this mechanism. Now, these are the commands that go in there. So it's command, data, command, data. As far as the data is concerned, this is a data payload for transaction data. Okay? And you can see there's a lot going on here. A lot of different types of messages. And the way that this structure is designed, it can handle a wide variety of data that you are sending. Whether you're sending individual objects, you're sending a text string, you're sending a blob of binary data, it's all in there. And I won't go through the details. of all this. If you're interested in the code, you're welcome to take a look at it. It's actually quite simple as far as kernel subsystems go. But what you need to know is this is the data structure. If you are trying to monitor what's going on with Binder, say you are using one of our tools like DroidScope, okay, and you want to build a plugin which monitors all Binder traffic that's going back and forth, you're going to watch for any system call that opens up dev Binder, and anytime an iocto call is made to that, you're going to pull that data structure that comes out of it, and you're going to pick it apart using this to see exactly what is inside of it and where it's destined for, what the actual payload is, and vice versa. When you're returning back from the iocto, you'll be able to see what's going on. So if you monitor everything that opens dev Binder inside the system, you can actually keep track. Okay, well, I sent this out from here and it popped out over here. Yeah, that sort of thing. And you can see exactly what the data is on both sides, and you can compare and see if it's been tampered with. This is passed through the kernel, or something like that. So a lot of possibilities if you're interested in actually monitoring what's going on in Binder. Pretty simple subsystem, but very powerful. So what you can do with it. Okay, so you want to learn more, I'm sure. Go ahead.
So is it the same path that the data takes? Even is there like different paths which take different overheads, or is it the same path through the kernel for any Binder calls?
Same path. Same path. There is a Binder subsystem inside the kernel itself. It's like a device driver. That's where dev Binder is exposed, and it's kind of like a routing switchboard post office. It sees messages that have come in and then figures out where they need to go. So they're all routed through that central switch. Now, it would be nice if we could just monitor messages as they pass through that central switch. And if you turn on debugging in the kernel, I think it's like /proc/binder, if you cat that out, you will actually see anything that's currently in this internal ring buffer as data is passing through, but it's transient. You only get a snapshot of what's happening at that point. But they will all pass through that central ring buffer inside the Binder subsystem inside the kernel. So it's all one central point. Okay. Okay, so if you want to learn more, if you're up for some punishment, the Linux kernel mailing list is generally the best place to find out anything that's going on. They're very impolite, but they're very knowledgeable. I wouldn't ask any questions on the mailing list. I would just read and search through their archives. And you will hear people debating all sorts of things and insulting each other's mothers over it and everything. It's great. But they're really the experts on what's going on inside the kernel. Maybe not Android specific, but also seeing how the subsystems of the Android kernel mesh up with the rest of the Linux kernel as a whole. Okay, the book Embedded Android is an O'Reilly book, fantastic book. If you're interested in this at all, porting Android to platforms, which is big money work, by the way. If you guys are like, why am I taking this class? Trust me, if you know this stuff, there are people ready to hire you right now. So get that book and read it. That Embedded Android book, the picture that I showed earlier of the flow through the Android system, going from the CPU to the bootloader to the kernel to init and everything, that came out of that book. And it's a very, very good book. So it explains a lot of the subsystems and what they're doing. So it gives not only a good high-level view, but also if you get asked in an interview question, okay, well, we have our platform. Where I want to dynamically load modules, where would I put it in the file system? I want to dynamically load firmware. Where would I put it in the file system? This book will answer all these questions for you. All those little details that you ask on a mailing list and no one seems to know, the book's got you covered. TI has their Rowboat project, which is the port of Android to their single board computers. The BeagleBone, the BeagleBoard, the BeagleBoard XM, the BeagleBone, the BeagleBone Black, the one that I did, they have a port to the BeagleBone Black now with a 3.2 Linux kernel. All that stuff is available at arowboat.org. And that's what I use as the base for my work, for the file system, user space stuff that's built for the Android system, as well as their make files were the ones that I was hacking on. And then for Binder itself, the Open Binder documentation, this looks kind of like a silly URL, like it's somebody's hobby page or anything. This is the actual web page for Open Binder, and it has full documentation on it. It explains all the data structures, all the communications, gives state machines, the whole thing. Okay, so if you're interested in Binder, that is definitely the place to look and read, and it's actually quite accessible. It's easy to understand when you're reading it. It's explained in plain English. It's not a whole bunch of technical jargon that you need to read something else before you understand what's going on. If you got the general understanding of what I've been talking about, you'll understand this documentation no problem. And it's very, very thorough as well. And I did compare the current kernel source against what's on here, and it's the same. So it is accurate. It's up to date. Okay. So as far as the PowerPoint, that's all I have. So are there any questions?
Where's the permissions checking done in this process? Like when you make a call with Binder interface, where does it check the permissions?
Well, if you're talking about permissions to access Dev Binder, or are you talking about
between processes?
For who you can send an intent to?
Yeah.
Okay. The handling of the intents is done by the framework itself. So think of it this way. When you make a call from inside your application, I want to send an intent. The first thing that happens is that intent object is passed to the framework, and then the framework will marshal it and put it in Dev Binder for you. The framework will say, okay, you want to send an intent to this. Do you have the permissions to do that? And then it will look at your manifest for that particular application, and it'll say, no, you're lacking this permission to send this intent to this service. So no, you can't do this. So really, it's the very first step of the process. You create an intent or whatever message that you're going to send, and then you try to send it in the framework, which would then marshal it into a data structure and send it through Dev Binder. Before it does that, it will check and see if you have the permissions to do that. There's the
transparent to the Linux kernel.
Oh yeah, it wouldn't even get to the kernel. It would get stopped by the framework before it even got there. The only thing
actually it's the other way. The permission checks done by the server, the service. So let's say you want to start activity, and then the framework will basically construct that intent as a binder message. Send that to the through the binder. Package manager as a service receive that intent. It will check, oh, do you have that permission to start activity? Oh, if not, then I will just reject it. And then it will basically pass back the result saying there's a security exception. They will raise that security exception through the framework, and if your application catch that exception, then that's great. Otherwise, your application crashed. So that's actually the other way.
Okay.
The reason for that is because the application itself is not trusted. The framework code within your application is not trusted. Okay, they don't trust that decision, so you don't make decision within the application. Security decision must be made outside. So that's a principle. So if you make a security decision within the application, then if the application is malicious, it can find ways to bypass that security check. So that's why it's actually the other way.
Okay.
So it's done outside the sandbox.
So it's in the framework, but it's on the other side.
Yes.
Okay.
So the Binder IPC is working synchronously. So isn't it a performance bottleneck?
I wouldn't think so, because really your overhead is the time it takes to marshal it and send it off through the kernel. Unless you have a lot of things that are spamming the kernel at the same time through Dev Binder, I don't really think it would be a performance bottleneck. Any IPC is going to be slow by its nature, but really you're not doing anything like, I wouldn't expect it to be any slower than like a pipe through the file system or something like that, because you're not really hitting anything other than memory, because then it is /dev/binder. Once you open that up, that's not a true file. That's just an interface to the kernel at that point. So you're really just swishing everything back and forth through memory. You're never writing anything out to disk. And since it's passing through the kernel, it's going to be pretty fast. So I think, like anything, if there is a lot of activity going on, if there's a lot of binder messages you're just sitting there spamming, you might be able to drag the system down just a little bit. But Binder does have throttling mechanisms in here, the max number of threads. So if you make an ioctl call to send to dev binder and the kernel is currently full up, it's like I'm already handling as many of these requests as I can have, then the ioctl will just return back with, try again later. It's like, it's failed. So it's slow by some standards, but not that slow. I don't think it's going to make too much of an impact.
So there are already some IPC mechanisms. Why do we need binder, or what's the advantage and disadvantage of binder compared with like sockets or pipe?
If you are doing any sort of inter-process communication through other mechanisms, it's up to you to explicitly specify your endpoints. You need to know who's going to receive that message. You have to do coordinated communications back and forth. Like if you're doing a pipe, typically you have a process that will set up a pipe and then fork, so the other process has the other end of the pipe. For something like Binder, it allows you to send messages via IPC communication without explicitly knowing the details of the endpoint that's going to receive them. You know enough about them to provide a general address that the kernel can then resolve, or the framework can resolve, to get it where it needs to go. So I guess the major advantage of using Binder is that you don't need to know all the details, you just need to know some of the details in order to make sure that a message still gets there.
Yeah, I think for the design of this intents, we have, most of the time we have two kinds of intent, right? Explicit and implicit. For explicit, probably you don't need this interface, right? But for the implicit ones, I guess it makes a lot of sense. So to just give to the binder to figure out who is
where it needs to go, like a broadcast type intent. If you were using something like sockets, everybody would have to be listening, and you have to send out like a multicast, or talk to each individual socket that's
But I
listening.
think there's a good question to ask, and also to find answer, which is just using that start activity as an example. It was first send to the package manager. Actually not so. Activity manager, right? Activity manager will figure out whether you have the permission, all right? And if you have the permission, who is the target process? And then basically forward that, maybe that's another intent call. Another binder message. Say, okay, you need to start that activity. Okay, but if you think about as an attacker, okay, if the attacker can just directly send the binder message, can the attacker just directly send a message to the target process without actually talking with the activity manager first? Is that possible, or is there any security mechanism to prevent this from happening? I guess there's something to investigate if you're interested. So as a core project, this can be one if you're interested. Okay, I just want to understand. Okay, Binder as a media, to basically convey all these messages. But is there any security issue? How the security checks are done? We know conceptually that what would happen, but is there any holes, vulnerabilities in there? Basically, as an attacker, if you can definitely directly talk to the binder. Nothing to prevent you from doing that, right? But if you can do that, is there any problem with that, right? That's a good question, actually, to ask. Yeah. Any other questions? So you're going to have some videos to show? Or?
Yeah, I can show some.
Yeah, you can use whatever, Chrome or just don't check my email.
Okay. Better off not knowing. Okay, youtube.com. It's the exciting part. We're going to watch some videos. Okay, so let's see. Android, HDMI. Oh, I thought I would have rated higher than that. Okay. Be a little bit more specific. There we go. That would be me right there. Okay, so this is you guys laugh, but I've already made about $50 in ads off this one video. It's like 3 minutes long. So when I first did my my port of Android to the BeagleBone Black, this is kind of like my final report that I gave to Dr. Du. Afterwards, when I first made this, I had a project from a previous semester on the BeagleBone Black that I grabbed the kernel from that and used that as a base, which is why you get the Beagle SNES flash up here. That's the splash screen from my other kernel. Getting the system up and running is actually pretty quick. I'm sure that looks familiar to everybody. It's a loading animation that starts up. It's completely customizable. You can swap that out. I just use the default one. But this is running over an HDMI video connection. So I have actually plugged this into a 1920 by 1080 display before and had Android on a huge screen and everything. It works. And it's completely scalable. I've also had it on 320 by 240 LCDs as well. So you can see it looks just like what you would expect from an Android. So this is more of, I guess you could say, the default type configuration. If you were to build an Android without any bells or whistles or vendor customizations, this is really the bare bones Android that you would get. And you can see it's running version 4.2.2, it's Jelly Bean, one of the newest ones. I had a physical Ethernet plugged into this because the BeagleBone Black has that. It will also do Wi-Fi if you configure the Wi-Fi drivers properly for it. And I was running, the whole file system in this case was running off of a micro SD card. So I had the data partition. If you have an Android phone and you put a micro SD card in it for storage, everything, you install your apps to that, that was just another partition on the file system that I had. So I had 4 partitions, I believe. One was the root file system, one for apps, one for boot, and then another for just general storage for whatever. On just a 4 GB micro SD card. You can see everything that you would expect is in there. And one of the important things I think about having a reference image like this to go and look at, like if somebody lays out the build process, if you can build a kernel and get it installed on your system, if you can build something like Android, something much bigger, and make a working system out of it, that opens up the doors for you to make modifications to the source code and start experimenting with it. If you can build it and install it and get it running, then that means you can make modifications to it, build it, install it, and get running. And that's when you can really start to experiment. If you're scared of these pieces, if you're scared of the kernel, if you're scared of building whole Android systems or whatever, then you're going to see the system as a series of black boxes that this goes in, this comes out, but you don't actually understand what's happening inside. So if any of you are interested in doing research in this kind of area, or if you're interested in doing work in industry in this kind of area, classes like these are really your chance to try building some of these components and getting a working system together, even if it takes a long time just to fumble through the logistics of doing it for the first time. It is extremely valuable experience for you, because this is your chance. This is why you are here. It is just a means to an end in some of your classes. I mean, some of you may view this as like, okay, what do I have to do to get a A- in here and move on because I've got 2 other classes I'm worried about. If you have that view on things, if you're only trying to get your classes out of the way so you can get your master's degree and then go on and get a job in industry, you're kind of viewing it the wrong way, because this is your chance to develop those skills that you will need. The reason that they want to hire master's students in the first place is because they want people that know this sort of thing. So if you can do it, or if you want to learn how to do it, this is your grand opportunity right now. You have people around that know how these pieces work and how to build this system, and can provide you with some direction and instruction and kind of get you going on this path. So when people say, do you know Android? And you go, oh yeah, I've built apps before. Well, big whoop. You know what? There are a million other people out there that know how to build apps. But I can guarantee you there's far fewer people out there that know how to build a kernel and get it installed and tinker around with these sort of things, write a new device driver, play around with the internals of the kernel itself, or maybe make a modification to one subsystem, some user space daemon that's running under Android, rebuild it, install it on your experimental system, take some measurements, get an idea of what it's doing, how it works. There's a lot of room to experiment here. So even if you feel like you're reinventing the wheel and you didn't get that much accomplished, it's the experimentation of it. It's learning how it all works, how the pieces work together, and the practical aspects of building it and getting installed on a system and running that are the valuable pieces of what you're going to get out of a course like this. So one other thing I will point to here is
Yeah, so Andrew made a very good point. The reason I leave like a month for the course project is for you to really to get some hands-on things done. Okay, we talk a lot of system architecture, design principles in the class, but if you don't do it on your own, you don't really learn the details. Okay, you just know some high-level messages, some high-level principles when you talk to people. Oh yeah, I know Android, Delphic virtual machine, Delphic bytecode, whatever, But if you tell people that I actually build it, I actually look into some specific, details, and I actually, hack something out of it, that's completely different. That's completely different. And there are plenty of the companies look for this kind of experts. So really, work hard, so get something done.
It'll pay off, guys. It will. We're not just doing this to torture you. We're trying to lead you in the right direction. So for the work that I did in Dr. Du's class and actually getting Android running on this, I documented what I did and have a full build process that says how to configure it, and building the bootloader, and explaining some details of the file system, how to build everything. So step-by-step instructions here. And people actually click that donate thing, by the way. I've made like $150 off this page so far. I'm like enthusiastic. I already paid for the hardware and everything. But yeah, there are directions out there step-by-step. And I'm the one who wrote these. So if you have questions about this or you run into problems, you can there's a person you can actually come to and talk to about this. normally you're kind of digging around on some blog on the internet and trying to find the information that you need, and you can't find it and all that. But anyway, so I think that's all I have, and it is 10:33 right now, so we've got an extra
We have some
15 minutes. So
minutes for discussing. Any more questions?
Question here. So I think you're using the HDMI to
Mhm.
display. So I'm curious about the display driver. You're just using the existing display driver.
Yep, it is using the TI-LCD driver, TI-LCDC, and that is a generic wrapper frame buffer driver for TI-based chipsets, for system on chip. It does the communications over the LCD pins and also the multi-channel ASP pins for audio. Well, actually, let me back up. The LCD pins are being driven by that TI-LCDC driver. It exposes dev FB0 in the file system. So you can open that up with any frame buffer graphics library that you're interested in. That will pass frame buffer data to the TI-LCDC driver. You can also do like FB set to set the resolution, that kind of
So
thing.
they actually support all kinds of those connection types, like a HDMI, like a display port.
Well, the driver itself, the frame buffer driver, will drive the LCD pins. Assuming that you have the signals, the LCD signals multiplexed to the physical pins on the chip, which are exposed by these connectors here that are on either side. There's a series of these pins which are available for LCD displays. So you can take an LCD board and just plug them into those, and it will receive, it's like a 16-bit data bus and then 4 control signals, I believe, 4 like timing control signals. On this particular board, there's an HDMI framer chip that is hardwired to those LCD pins. That framer chip actually generates the HDMI signal. So the TI-LCDC frame buffer driver connects to the chip, the HDMI framer chip, and there's a separate driver for that. Likewise, there's an ALSA audio driver which hooks into the HDMI framer chip driver to supply the audio side of things. And those go over the multi-channel ASP pins, 4 of those. It's like one data and 3 clocks you run across it. So all of this funnels into one chip, which then goes up the micro HDMI port. Yep.
Do you find any online cross-reference for Android source code, like Android kernel source code?
Not anything other than just digging through the source code itself. That embedded Android book had some information that kind of gets you pointed in to the right subsystems. When you are porting Android to a new platform, one of the user space components that you need to worry about, or one of the components of the system as a whole, is what they call the hardware abstraction layer. And you can think of it as the mapping between the kernel-specific stuff that's exposed via the device drivers that are in the kernel, and then things in user space. So if you have a framework for Android that plays audio, eventually at some point it's going to open some audio device in the /dev file system. But you don't want to slightly tweak your framework for every different variant of phone out there. But what you can do is put a hardware abstraction layer in there, which exposes a common interface for making audio calls, and then on the other side of that hardware abstraction layer, it talks to the actual /dev/whatever. So if you are looking at a particular implementation of Android for a platform, like for this, generally the hardware abstraction layer is pretty well documented, because that's one of the things that people are interested in. If you're interested in the higher level stuff that sits on top of that, that's more generic across every Android system, an O'Reilly book on Android would be the best way to go. That'll give you a high level tour of what's there. You can also dig through the Android web pages, and it's what, android.org or whatever, that actually hosts the top level stuff, or android.kernel.org. But for that, you really have to know what you're looking for in order to find it. If you're looking for a general introduction, where is this? I want to know where this is and everything. The embedded Android book would be my recommendation. It's pretty accessible. Plus, you can just zip to the index in the end if there's something in particular. I want to know how to do video. I want to know how to do this. You just flip to the back, look where the comments, and then go from there. But the documentation that's out there on the web, it's the way I look at it, it's free for a reason.
It's confusing. It's really confusing over there. Means everybody said some different things. I was digging into trust zone code, but I would never get to it.
Oh, ARM trust zone?
Yeah.
Oh, good for you. Yeah. Very, very nice. Very slow on the context switch, but it's good for good base level attestation for security on it and everything. But it's good. It's good. Yeah, I've heard that there was a series of trust zone patches that just made it into the kernel recently. So hopefully that'll become a bit more mainstream.
I couldn't get more far because there are no such resources available now.
Yeah, there isn't. The best that you could hope for is to try to dig around through ARM holdings stuff, because the ARM processor is not made by like ARM. What they do is they have the ARM instruction set available as a reference implementation, and then somebody who wants to make an ARM chip, they license that IP from a company called ARM Holdings. So ARM is really just designed for, or their purpose is to make an instruction set and write sample implementations and provide them to people, and then they get a license to get like maybe a penny or 2 cents per chip that for every chip that's sold that uses their design implementation. So trust zone technology is you can think of it as you can put a core, an ARM core, into a trusted state. Its memory is completely partitioned. It can't be physically accessed by another core. So you could have a program that has 4 threads running on 4 different cores, and one of which is put in this trust zone state, and it completely isolates it, different registers, different memory space, everything. So there's no way that you can get into that chunk of memory that's allocated to that secure context inside of the trust zone core. And you can flip any process at any time, or any context, from secure to unsecure, and it'll completely swap out all the registers and bring secure versions in and everything. So there's no way. It's completely isolated. The downside is it does take a while to do that context. The context switch is very expensive in terms of time, so you wouldn't want to do it all the time. But if you had one particular context running inside of trust zone, and then everything else outside of it, you could use what's in trust zone to do attestation, to attest that something is valid, it has not been tampered with, because whatever's in the trust zone can't be tampered with by the outside world. So it's an interesting technology. It's in ARM processors, some of the newer ones. Anybody else?
One quick question about, do we have any browse like Google that we have in the OS class that we can do identifier search for the functions in the kernel source?
Oh, I'm sure you can dig around and find that. You're talking about where you go into FreeBSD and it gives you a code listing, and every structure is a hyperlink to where it's located and everything.
I don't think that's what I was asking you.
There's
nothing like that.
I didn't find it.
Yeah, you're not going to find the entire Android source code duplicated online in HTML format with links. That's not going to happen. You will get some references online to specific subsystems, but not a huge cross-reference document like that, because FreeBSD is a lot slower moving, and it's more of it's designed to be well designed. Android is designed to get the job done, so it changes a lot, and no one's going to keep that documentation up to date online.
Any other questions? Yeah, the point is we have lots of, we're not just talking about the abstract concept. We have the work. We're working on those things. We have tools to do static analysis. We have tools like JavaScript to do dynamic analysis. We have these, things that can actually help you to customize the kernel and port it to certain hardware chips. Things like that. So, do these are the examples. So if you want to continue or do some further investigation on those tools, go ahead. Okay?
Also, has anyone here not taken the operating systems class yet? You can admit it. It's okay. Okay. Oh, are you guys in for a fun time? You can think of this as, in some respects, as OS Lite. If you do a good job on the project here, you're probably going to have a much easier time once you get to the operating systems class. And trust me, when you get to the OS class, you need all the help you can get. So this is your chance for a warm-up before you get in there. If you have to take the OS class. I don't know if you do or not. If you're in, are you CS, CE? Okay. Yeah, if because I think the CE people can kind of get away without doing operating systems. They can choose a different track, which is probably what a lot of you have done. But for computer science, it's one of the core classes. You have to take it. So have fun.
Yeah, I think the point is that it's not to just get away with those courses. You're here to learn things. So it doesn't matter whether some courses are difficult. It's difficult for a reason. If it's difficult, you can learn things. Some courses are easy, you can easily get A, but you don't really learn something, know anything. So, right. Anyway, so yeah. If there's no more questions, then there was one
question. So the open binder, does it go locking when you how does it prevent race conditions when multiple?
When you make the ioctal call to the kernel, okay, that will be a blocking ioctal call. So the kernel knows how many incoming messages it has. Remember, the dev binder is just a front end to the device driver itself. So the device driver will only spawn as many kernel threads as it can handle internally, and it knows when requests are coming in. Because if you try to do an ioctal call to dev binder from user space, on the kernel it says, okay, there's an incoming call, but I can't handle it right now, so just let it continue to block while I handle what's going on. So really, it's kind of first come, first serve. Internally, there is a queue, where a message queue inside of the dev binder subsystem. And as messages come in, they're stuck in there. That queue itself, there's not a race condition on it. There is locking on it to handle it. I think it's very lightweight locking. It's like a spin lock or something like that. So as they come in from various threads from different places, that queue is still going to get locked and it's going to be popped in there sequentially. So no, there shouldn't be a race condition in there. That would be actually a pretty serious problem if there was.
So it's a global lock.
Yeah. It's a lot. Any shared resource in the kernel is going to have that lock on it, the spin lock. So.
Okay. So that's all for today.